My name is Chris Conlan, and I'm representing myself, Teddy Cunningham, Gunduz, Demirci, and Hakan Ferhatosmanoglu to present our work, Collective Shortest Paths for Minimizing Congestion on Temporal Load-Aware Road Networks. In this work, we're proposing a set of algorithms to provide navigational routes for vehicles in cities, which are proactively avoiding congestion and can reduce average journey times. We're motivated by the principles of altruistic routing, where it's better to find routes for vehicles that optimize at the city level to positively impact journey times in urban life. We also consider the problem in its abstracted form, finding shortest paths in a dynamic network. It's intuitive that when we answer one shortest path query, it'll affect the edge weights and costs of subsequent queries, and similar paths will cause congestion. We therefore propose that we handle shortest path queries collectively. The problem is a real one. Congestion affects virtually all cities. It has a significant impact on the economy as well as citizens' well-being, and in many cities, building extra road capacity is an extremely expensive option or not an option at all. Our study sits within a broad range of related studies, many of which have been published at this workshop in previous years. For instance, to address the problem of congestion alleviation, route diversification is a common approach in which users of similar OD query types will be returned a route from a large selection of diverse possibilities, such as Cheng et al.'s 2019 study, which ensured routes were returned with high spatial diversity and low cost diversity. Dynamic user equilibrium is another popular approach inspired by the principles of a user equilibrium on a road network. These approaches route and then reroute vehicles in flight, responding in real time to network conditions. Altruistic approaches are also popular. In 2020, Motalevi et al. Proposed an algorithm which maintains a heat map over the network to represent current network conditions and use historic network information to project forward in order to provide a system optimal routing. So now I'm going to describe the temporal load aware setting, which is the setting in which our algorithms operate and is an extension of existing temporal networks. We use this setting to model transitions within the network, to determine future edge states within the network, e.g. to identify if edges are in free flow or if they're congested, and with which our algorithms can easily interact in order to return shortest paths. So I'm going to describe the edge load matrix, the dynamic arrival time function, and how and why we demonstrate FIFO compliance. So the edge load matrix is the data type we define, enabling us to track expected future load with respect to time along each edge within the network. In doing so, we can identify where and when congestion will occur and design algorithms to proactively avoid it. In this example, we present a simple network over 3 time steps, and we can observe load building up. Red edges denote congestion. Crucially, we can observe the future state of the network from previous time steps. So if all the load in this network is from queries we answered in t equals 0, we can observe where and when congestion will occur in the future. Next, we discuss the arrival time function. This is a function that operates on each edge independently. So given the time that a vehicle enters the edge and the expected load, the function will return the arrival time at the end node for that edge. Our algorithms make dynamic calls to these arrival time functions as they compose part within the network. We use a nonlinear function that progressively penalizes load along an edge more and more as congestion builds up. A major benefit of using an arrival time function on each edge is that it's very space efficient. So for instance, we do not need to maintain a separate impression of the network for each individual time step. The FIFO property, which means first in, first out, or another way of saying this is that vehicles enter and exit edges in the same order, is an important characteristic in any temporal setting. This ensures that shortest paths can be discovered within the network. In this diagram, we demonstrate the behavior of an example edge under different load conditions given by our arrival time function over multiple time steps. We can see that the arrival time is always increasing even between time steps, which guarantees the FIFO property. We provide a more rigorous proof for this in the paper. Now I'll talk about our solutions. So firstly, we propose a set of algorithms to solve the standalone shortest path query in a temporal load aware network. These are algorithms that can dynamically and proactively avoid congestion. Next, we use these solutions as the engine for a collective solution to return an optimal set of routes by iteratively searching for paths with the lowest arrival time. we note here that chronological processing of queries does not guarantee an optimal result. After each query is processed, we update the edge load matrix, which therefore affects subsequent queries. A more advantageous ordering is likely to be achieved with a smart heuristic. So firstly, I'm going to present temporal load aware A star, which is one of our standalone shortest path algorithms. So the A star shortest path algorithm is an adaptation of Dijkstra's shortest path algorithm, which uses an expected cost function to direct its search towards the destination node. We adapt A star to operate within a temporal load aware setting. At each iteration, as we search the network, the cost to explore the neighboring node is given by our dynamic arrival time function, which is dependent on the edge load matrix. Thus, the algorithm is aware of expected future conditions in the network, and it can dynamically and proactively avoid congested routes. In this way, queries past and present are interacting via the ELM, the edge load matrix. The solution guarantees that the shortest path is discovered for any distribution within the ELM. So next, I'm going to describe the temporal load aware top K algorithm. So this has been designed primarily for efficiency. So we pre-compute the K best free flow paths, and at execution for a shortest path query, we calculate the expected arrival time for each of these paths. This calculation uses the dynamic arrival time function, which is dependent on expected future load within the system. We assign whichever path returns the lowest arrival time. We note that queries are processed chronologically, and that after each query is processed, its path is added to the ELM. So now I'm going to present our collective solution for processing a set of queries, which we call the collective search for a minimal arrival time, or CSMAT. We utilize one of our standalone shortest path algorithms as the engine for this solution. Our preference would be temporal load aware A star, but any is fine. At each iteration, we're identifying a candidate set of queries, amongst which we will find the query with the lowest arrival time. And this is the query that we will assign. To do so, we calculate in parallel the temporal load aware arrival time of each query in the candidate set. We track calculations between iterations to reduce redundant calculations, and we use machine learning to restrict the size of the candidate query sets. CSMAT has been designed to be embarrassingly parallel in order to ensure scalability. So now I'm going to take you through how CSMAT operates. On the left-hand side, we have the flow for the overall algorithm. So we want to input the network, the query set, and the ELM, and we want to return a path set, which is a path pertaining to each query. So first of all, we sort the queries by their free flow arrival time. This free flow has been pre-computed, so it's readily accessible. We then select the next query in the query set, which we're going to process. And we're going to test this query's free flow path to see if any of its edges are congested. If none of the edges are congested, then we know it must be the path with the lowest arrival time, as we've already sorted the query set by free flow arrival time. If any edge in this path is congested, we now need to collectively search for a query in the wider query set that gives the lowest arrival time. So we move on to the flow on the right-hand side. So often we will find ourselves processing and reprocessing the same query again and again if the base query in a particular iteration did not return the lowest arrival time. So we test for this. And if we observe a query for the first time, then we must select a candidate query set Q-. We use machine learning to predict the arrival time of all the queries, and then we select those queries into Q- whose predicted arrival time is within an acceptable range of the base query start time. We then calculate in parallel the temporal load aware arrival time for all of the queries in Q-, for example, using temporal load aware A star. If we are reprocessing the same query, we only need to recalculate the temporal load aware arrival for a subset of Q-. That is, those queries who have any spatiotemporal intersection with the previously assigned path. Once we've assigned the query with the lowest arrival time, once we've identified the query with the lowest arrival time, so we're moving back onto the flow on the left-hand side, we assign this path, we update the ELM, and we move on to the next query until we've processed every query in the query set. The calculation of a query's arrival time in the collective operation only depends on the ELM, which is updated outside of the collective processing. Thus, it's static at the point of processing, and this is how we ensure the process is embarrassingly parallel while also collective. So now I'm going to discuss our experiments. So we've run a set of experiments on real-world data in the cities of Porto and New York. We take the road network from OpenStreetMap and queries as representative taxi trips from these respective cities. We simulate congestion by selecting different query set sizes in each city, but within the same time range. And we use the following metrics to understand performance: average journey time, which is the average journey time for each path in the path set; load distribution, which gives the average percentage of edges in the network that are utilized within each time step; and free flow capacity utilization, which gives the proportion of free flow capacity in the network that's being utilized. So here we're going to investigate the effectiveness of the standalone temporal load aware shortest paths, and we compare it against two baselines. First is the free flow naive Dijkstra, FFND, which is a Dijkstra algorithm which uses the free flow edge weights. And next is the static load aware Dijkstra. This operates a version of Dijkstra that can respond to network conditions at the point at which the query is asked. And we understand this is similar to how proprietary methods like Google and TomTom operate. So we can observe that our algorithm temporal load aware A* is the best performing solution in all scenarios. Our analysis also shows that this algorithm improves as congestion improves up into a point, and then the benefits start to plateau. And this is probably expected behavior as it becomes harder to find viable alternative routes in extreme condition. Next, we investigate the benefits of collective processing. We do this by comparing CSMAT to the standalone algorithms where the queries have been processed chronologically. We observe that CSMAT outperforms all the algorithms across all scenarios, and these savings can be in the region of minutes per query, and they aggregate to significant savings at the city level. So we know that not all users will take their recommended routes, and that operators only have a certain amount of coverage. So we've run a set of experiments where only a subset of the users are under the control of our algorithms. In effect, we have competing algorithms. We continue to note that CSMAT is able to reduce average journey times even at lower levels of control. And an important finding is that where there's a mix of algorithms, the traditional methods used by Google, etc., deteriorate rapidly at lower levels of control. This would be a major disadvantage for an operator who does not process queries collectively when others do. An important metric is how well we are utilizing the road network. We can observe that CSMAT is able to achieve very high levels of network utilization and can reach a high diversity of edges within the network. One thing that we note is the very different profiles of network utilization between the cities, and this may motivate further studies for bespoke algorithms for different types of network. Finally, we consider fairness and plot the distribution of the user level congestion penalties within each system. We can observe that temporal load aware A* returns a very fair distribution that tends towards a Gaussian distribution. No user in this system is treated significantly worse than any other. CSMAT has resulted in a less fair system in which some users are receiving large congestion penalties. This is the cost of collective processing and warrants further study. So future directions of work may be to optimize our existing solutions for fairness. We may investigate the possibility of integrating it with dynamic user equilibrium approaches, or potentially using agent-based modeling, things like reinforcement learning. And we summarize our contributions as follows. So we have formalized the temporal load aware setting. We have made adaptations of classical shortest path algorithms to operate within this temporal load aware setting. And we propose a scalable algorithm designed to return system optimal routing for a batch of queries. Thank you very much.